So we discussed semaphores and their role in synchronization. However, the traditional semaphore operations, wait and signal, suffer from busy waiting, where processes continuously check the semaphore status and it consumes CPU cycles unnecessarily. To resolve this, we introduced a more efficient mechanism. We defined semaphores like C structures, making use of two essential operations, blocking and waking up. So we represent a semaphore as a structure that includes a value and a list of processes. When we use a semaphore, we can perform two primary operations, block and wake up. Blocking puts a process into a waiting queue, okay? While waking up takes a process from that queue and moves it into the ready queue. And now when we talk about wait and signal, it's all about modifying the semaphore's value. When a process calls wait on a semaphore, it decreases the value. If the value goes below 0, the process gets added to waiting list and it's put on hold. Okay. So when we signal, we increment the value. If the value becomes greater or equal to 0, it's time to wake up one of those waiting processes. This way, semaphores help us manage and control the synchronization of process in a structured and organized manner. In this modified approach, when a process executes wait, okay, and finds the semaphore non-positive, it blocks itself instead of busy waiting, okay? So the process is placed in a waiting queue associated with the semaphore and its state changes to waiting. The CPU scheduler then selects another process for execution. And when a process executes signal, it increments the semaphore value. And if the value is non-positive, indicating waiting processes, one process is removed from the waiting queue and switched to ready state. So state switch to ready. Actually, this allows for more efficient use of CPU resources. Yeah. So semaphores in this context consist of an integer value and a list of waiting processes. When a process needs to wait, it is added to waiting list and the wait operation decreases the semaphore value. And if it becomes negative, the process is blocked. The signal operation increases the value. And if it's positive, the waiting process is awakened. Okay. So it's important to note that under this approach, semaphore values can be negative, indicating the number of waiting processes. So in this modified semaphore approach, we have effectively reduced busy waiting. However, it's crucial to acknowledge that we haven't entirely eliminated it. So busy waiting has been shifted from intersection to the critical sections of application programs. So the busy waiting now occurs within the wait and signal operations, which are typically comprising about 10 instructions if coded efficiently. The advantage lies in the infrequent use of the critical section. Actually, due to its nature, busy waiting rarely happens, and even when it does, it lasts for only a short duration. This design works well for applications where critical sections are short and not frequently occupied. However, it's worth noting that in scenarios where critical sections are long, spanning minutes or even hours, or when they are almost always occupied, this approach becomes inefficient too. In such cases, busy waiting can significantly impact system efficiency. Now, let's talk about the types of semaphores. So they come in two main types, counting semaphores and binary semaphores. And in counting semaphores, they use integer values that can span an unrestricted domain. And binary semaphores, on the other hand, have integer values that can only be 0 or 1, essentially representing Boolean values, okay? So their simplicity makes them easier to implement and understand, and binary semaphores particularly just as like mutex locks. So, however, using semaphores does not provide perfect solution. They also have some drawbacks. So proper usage of semaphores is crucial. Mistakes in the order of operations can lead to synchronization errors. So all processes involved must use semaphores correctly. A single misstep in any process can disrupt the entire system synchronization. So we can say that they have complex usage. We need to be careful about that. And a single malfunctioning or malicious process can jeopardize the synchronization of the entire group of processes, highlighting the delicacy of semaphore implementations. So they are also vulnerable. So let me explain the first item in detail. So in the semaphore-based solutions for critical sections, processes use a shared variable called mutex, set to 1 initially. Each process needs to follow a strict order. It must wait before entering the critical section, okay? And signal, yeah, and signal after leaving it. If this order uh, If this order isn't maintained, multiple processes might access critical sections at the same time. Even a single process misbehaving, whether due to errors or intentional actions, can cause these problems. To prevent these issues, it's important to be careful and strictly follow the synchronization rules. So common errors include signal mutex followed by wait mutex and redundant wait mutex operations, or omitting of either wait mutex or signal mutex, or both of them entirely. So in semaphore-based synchronization, adhering to correct order of operations is very important. If this order isn't precisely followed, timing errors can occur. So researchers have addressed these issues by creating high-level language constructs. One essential construct is the monitor, a fundamental high-level synchronization tool. So monitors act as a convenient and efficient mechanism for process synchronization, allowing only one process to be active within the monitor at a given time. So various type of monitor exist and they are found in popular concurrent programming languages like concurrent Pascal Modula 3, U, C++, and Java. Interestingly, monitors can be implemented using semaphores. So next week, we will explore some classic concurrency problems. We'll examine the producer-consumer problem, which involves balancing data production and consumption. And then we will explore the readers-writers problem, where multiple readers need access, but writing must be exclusive. Lastly, we will see dining philosophers problem, which focuses on sharing resources without encountering deadlocks.